Hi, my name is Shonichima, and today I'll be solving Leetcode problem 724, find pivot index. So for this problem, we're given an array of integer nums, and our goal is to calculate the pivot index of this array. And it says here the definition of a pivot index is the index where the sum of all numbers strictly to the left of the index is equal to the sum of all the numbers strictly to the right of the index. And it says here, if the index is on the left edge of the array, then the left sum is 0 because there are no elements to the left. And this also applies to the right edge of the array. And it wants us to return the leftmost pivot index, and if no such index exists, return -1. So the leftmost pivot index would just basically be the pivot index here, where I previously just explained what they meant by pivot index. And for examples, for the first example here, we're given an integer array consisting of these 6 numbers here, and the output is 3 because we can see here at index 3 the sum of the elements to its right, 5 and 6, is 11, and when we add 1, 7, and 3, we also get 11. So 3 is the pivot index of this example. For example 2, in this case, there aren't any pivot indices, or there isn't a pivot index because there's no possible index where the numbers to the right side of the particular index are equal to the numbers to the left side of that particular index. And for example 3, the index in this case, or the pivot index in this case, is 0 because all the numbers to the right side of that index add up to 0, right? When we take these 3 numbers here, or these 2 numbers here, we get a 0, and as a question defined over here, if the index is on the left edge of the array, then the left sum is 0. That's why, in this case, the pivot index is 0. So, with that being said, let's talk about how we can solve this problem. So, similarly, like to many other problems, there is usually a naive way to go about solving it, and then there's an optimal way to go about solving it. So I'll be talking about the naive method first. So the naive method here would just be to iterate through our entire array, and on every iteration we just split our array into a left partition and a right partition. Then when we do that, we can just find the sum of both partitions, and if at any point in time the partitions of both sums are equivalent, then we can just return that particular index. This is a naive solution, but the time complexity of the solution is polynomial. Why? Because we're going to have to iterate through our array, and as we're iterating, we're partitioning our array into 2 subarrays. Now, when you partition an array into 2 subarrays, you're technically doing another iteration to gather all the elements up to that particular index that you're on. So that is another n operation to do, thus making that particular solution polynomial. Now, how can we optimize this solution? To optimize this solution, we can use a very nifty method here, a very nifty way around the naive solution. So what do I mean by this? We know that we still need to find a way to calculate our left subarray sum, and we need to find a way to calculate our right subarray sum. So we can actually just keep track of our left subarray sum, since we're going to be iterating through our array from left to right. We can keep track of the sum as we iterate through our array. So for example, when we start off iterating from our input, we know our left subarray sum. So left sub sum equals to 0 when we're at this particular index. Now, when we increment our left pointer to the next index, our left subarray sum updates to 1. And as we continue to do this, we can keep track of our left subarray sum. Add 7. And I'm going to do this all the way to our third index here. Then we add 3. So adding these three numbers together, we get 11. Now, we also need to calculate our right subarray sum. And how do we do this? So if we were to calculate the total sum of this array, we know that our total sum will be 28. So how can this help us find the sum of our right subarray? So our sum of our right subarray at index 3 is basically the sum of these two numbers, right? So why don't we take our total sum and subtract the current element that we're on, because by doing so we know we're going to have the total sum of our left subarray and a total sum of our right subarray put together. So initially our total sum was 28, but then now our right subarray sum can equal 28 minus 6, which is 22. Now when we have this number 22, in order to find our right subarray sum, what do we need to do? We need to divide this number by 2. When we divide this number by 2, what do we get? We get 11, which is going to be the sum of 5 plus 6. And that is essentially how we're going to calculate our right subarray sum as we iterate through our array. Here, I'm going to have our left subarray sum is 0. So we iterate through our input. Range 0 to len nums. And as I said previously, we only keep track of our left subarray sum if we're not at the edge of our array. So if we're not at the left edge of our array, so if I is not equal to 0, then we could update our left subarray sum to the previous number in the array by adding the previous number in the array. Alright, and to calculate our right subarray sum, we need to take our total sum minus the current element that we're on divided by 2. And how do we get this total sum? So to optimize this solution, we can just calculate this, the total sum outside of our loop by doing something like this, an nifty function in Python. Just sum our input by that. If you're not using Python, you can do this manually by just creating another for loop. And once we have this, we can just say if at any point in time our left subarray sum is equal to our right subarray sum, then we found the pivot index, and we can just return that particular index. Now in the case that we never find that particular index, we just need to return -1. Let's run this code and see how it works. So this passes all the test cases here. If I submit it, see if it's accepted, and this is accepted. For the time and space complexity, we see here that our time complexity is O of n because we're initially using one loop to calculate the sum of our input, using another loop, and within this loop we're only doing O of 1 operations by doing simple conditional checks and simple updates to our left subarray sum and our right subarray sum. And in terms of space complexity, we're not using any auxiliary space, so our space complexity is O of 1. So our time complexity here, O of n, and our space complexity here, O of 1. And I hope this answered any questions you might have had about this problem here. If you continue to have any more questions with this problem, don't be hesitant to leave a comment down below, and I'll be quick to respond. And don't forget to hit the like and subscribe button, and have a good day.